Okay, I think we can get started. Good afternoon, everybody, and welcome to this webinar organized by the South African National Group of IAPSI. The title is really a question, and it is 3D printed concrete increasing quality and productivity? The presenters today is from the 3D print concrete research group at Stellenbosch University here in South Africa. And they'll be sharing their research and what they've learned on 3D printed concrete. Just some notes, this webinar is being recorded and it is being streamed live on YouTube for the first time, IAPSI's YouTube channel, so it's being streamed live. After the webinar, it will be placed under e-learning on IAPSI's website. You would have seen the list of presenters in the advertisement. I just want to announce two replacements. So Jacques Kruger will take over for Gideon van Zijl as the main presenter and the moderator, and Wiebke de Villiers will stand in for John Babafemi. We are fortunate to have a sponsor today, and our sponsor is Chryso Southern Africa. And Chryso is not only a local company, but a global company that operate in construction chemicals. They are solutions driven and dedicated to low carbon emission products. They're a global leader in innovation and performance, and they're globally part of the Saint-Gobain group. Their main products are plasticizers, super plasticizers, microfibers, accelerators, surface treatments, and retarders. So please have a look out for Chryso's products. That's za.chryso.com. That will be the local South African website, but I'm sure you'll find the global website quite easily. I'll now hand over to Jan Wiem to say a couple of things about IAPSI, and after that we'll commence with the webinar. Jan, are you there?
I'm here, thank you. Can you hear me?
Yes.
Good day, and thank you, Pierre. Thank you for this opportunity. I'll just say a few words about IAPSI as organization, for those of you who are not familiar with the organization. As you can see on the slide, IAPSI's mission is to advance knowledge and practices of structural engineering worldwide. Now, many people think that IAPSI only considers bridges, but that is not true. IAPSI considers all aspects of structural engineering, large, small, interesting, various materials, and any aspect of construction. So the members, quite a large number of members throughout the world, are members from industry, consulting environment, client, owner organizations, contractors, but then also academics. And that is what is so interesting about the organization, is that it is represented by all of these different factions. Thank you, Pierre. Just move it on. Oh, there you are. All right, so one of the big events or items that IAPSI organizes are conferences, and upcoming conference very soon is in the end of April, the IAPSI Symposium in Istanbul. And this is actually at conferences where IAPSI members really get the real benefit of membership. My own experience is that one may be a member for several years, but it's only when you start attending conferences that you really meet the people and start rubbing shoulders with other like-minded people. It is really a benefit to meet with people that share your same beliefs and your same passions, and also meet people that work on interesting structures, and you start realizing that all of them are actually just real people. So I encourage you, if you haven't attended our IAPSI conference, start going there. The first one, you may not meet all that many people because you may be new, but from the second, third one onwards, you really start building good friendships. Also, the Congress later in the year in Delhi, people are also invited to register for that one. So both Turkey Istanbul soon coming up, and Delhi later in the year. Here you can move it on. IFC has got a variety of offerings. One of them probably is the journal Structural Engineering International, which is a fantastic publication. It shares information about research, but it's also one of the best journals in the world that shares information about projects and case studies. So an interesting journal because academics publish in there, but it's also published, also information published by practitioners with good information about real projects. So if you're not an IAPSI member yet, make sure that you get hold of the Structural Engineering International. There are some other publications such as conference proceedings, case studies, and guidelines. And the structural engineering documents, as you see there, it's a series of documents that arrive from time to time on interesting structural engineering aspects. Thank you, Pierre. IAPSI is administered from out the office in Zurich in Switzerland, but the real work is done in the national groups. I'll say a little bit more about that in the upcoming slide, but what I want to mention here is the concept of task groups. A few years ago, IAPSI embarked on the concept of creating or allowing people to create task groups. A task group is a mini committee where 2 and more people decide on a topic which they want to address. And the concept is that one should decide on an outcome within 2 or 3 years, such as a publication or a journal publication, or even one of these structural engineering documents. And anybody can be a member as long as it starts with an IAPSI member. So you can also invite non-members to form part of this mini group with the outcome in mind. Thank you, Pierre. These task groups resort under a number of technical commissions who coordinate that, and you see the names or the topics there. I'm not going to run through that, but that gives you an idea of the type of topics that are addressed, and you're welcome to make contact with the administrative group in Zurich to offer some suggestions of topics you would like to investigate with your task group. Thank you, Pierre. There's a young members initiative in IAPSI, so all of the symposia and conferences always have events also for young engineers. In many of the national groups, there are very active young engineers groups. And if you are today listening and you're not part of a group where there is a young engineers program, make contact with a national chair, because it's really here where people start getting the concept of IAPSI, and from where you start meeting mentors and other interesting people that work on structures they've been working on structures for many years. So you see a list of things that come up there as young members, exciting initiative. Thank you, Pierre. You can move on. For several years, IAPSI has been building on the IAPSI e-learning platform, which captures videos and lecture series and lecture slides of keynote presentations at conferences, but it also includes information about other lectures and interesting topics. So as a member, you have access to the e-learning site. Please visit that. If you're not a member yet, this is a real valuable benefit of members, and something to be made use of. It is very useful also for lecturers to use as examples and information to students. Thank you, Pierre. Right, I mentioned the national groups earlier on. Most of the events that take place in IAPSI, such as this webinar, is organized on a national group level, but the national groups also organize in the bigger events. So this is really where the work starts, but the concept is still that national groups would collaborate worldwide and that you could meet people from around the world. So if you're not a member yet, make contact with the national group and the national chair. That can be done through the IAPSI administrative office in Zurich, or if you have the local contact details, make sure that you make contact with them. Thank you, Pierre. I mentioned some of the benefits. One of the tasks that national groups have is the concept of IAPSI awards. Annually, there's quite a number of awards, such as the best structures, the Young Engineer of the Year. There's also prizes for the best journal paper and so on. So all of these are initiated at the national group level. We make recommendations to IAPSI International for the award of the awards. Thank you, Pierre. Right, I think that brings me to the end, and I'm going to hand back to Pierre. Thank you for the opportunity.
Thank you, Jan. I'm going to now hand over to Jacques to start off the technical proceedings. Thanks, Jacques.
Thank you, Pierre. Pierre, can you just confirm that you see my screen?
Yes.
Okay. All right, welcome to all the participants to this webinar, and thank you for attending, where we will attempt to answer whether 3D concrete printing increases the construction quality and productivity. So everybody's welcome to pose questions in the Q&A section. Then we will answer these at the end of the presentations. So to answer the first question, the perspective matters on whether, the first perspective is whether it actually matters, right? So, or perhaps whether we are ready to answer based on actual data. So the 3D concrete printing global market value reached roughly 0.01% of the global construction market in 2022, according to the market research reports. And it's projected to reach 0.05% by 2030. So if you look at the solid symbols, they denote the actual markets, right? The hollow symbols denote the projections. So a very interesting finding is that the 2018 projection for 2024 was already exceeded in 2020 as well as 2022 by a factor of 10, which tells you that it's really ahead of the curve and it's growing rapidly. Now, as a disclaimer, we are not economists, we are engineers, and we did not check the cited market reports, so or methods of data collection and projection, but certainly the trends are there. Now, to give a perspective on construction printing as a portion of 3D printing. So from 2022, the concrete printing industry was 7% of the 3D printing industry's market share. But this is anticipated to grow to 9% in 2030. Now, if you look at the compounded annual growth rate of 3D concrete printing, it far exceeds that of just the printing industry. Now, this tells us, and it confirms that architecture and construction was included as a 3D printing technology in the larger printing industry. So the third slide is from a literature review by Bester et al. It's actually a current PhD student at Stellenbosch University. And it shows information that he obtained from a PRISMA process, which refers to the preferred reporting items for systematic reviews and meta-analysis. Now you can see the legend on the top left. So it gives you a clear indication of when all these were obtained. So how it was obtained was basically as a keyword in the publications, and then ranked them according to the cumulative number of times it appeared in publications. Now, relevant to this topic, the first one that we can see is that it's faster. So it's faster construction, decreasing the construction duration. Secondly, it's cheaper. So it decreases the construction time. And thirdly, it increases quality of precision, which you can see only was seen in 2020, relatively later on. So today we shall try to answer from all the available evidence whether this realizes in actual 3D concrete printing construction. Now, the question is relevant given reported stagnant and decreasing productivity in construction, while it has increased in other sectors. So if you observe the light blue line, that indicates the total factor productivity for the total United States economy, or GDP. And there's been a steady increase from 1950 up to 2019. But if you compare that to the lighter red line, you can actually see which refers to the total factor productivity of the construction industry. You can actually see that it increased from, say, the 50s to the end of the 60s, but then it just went one way, and that is down. Now, it must be added that this does not indicate the total number of projects or the market size. It refers to productivity. Now, productivity can be measured as an output from a given input. So 3D concrete printing has been motivated as a way to overcome labor shortage and cost through automation. So in developed countries, for instance, the United States, we see a decrease in the inputs and maintaining or exacerbating the output, so thereby increasing productivity. The construction sector, for instance, is not as lucrative as other automated sectors. While in developing countries like South Africa, with high unemployment, we're sitting at currently at more than 30%, and a housing shortfall, the output is increased more than the input, which is also increased. So that means that we employ more and we build even more. But luckily, a sobering finding by Bjorn et al., which was a survey in South African construction industry, indicated that not only technology influences productivity in construction. So what data is available in the 3D concrete printing construction to assess the productivity and quality? Well, little, but it's growing. So we see an exponential growth in 3D concrete printing patents, which was 108 in 2021. Papers stood at 430, projects 212, and enterprises or companies, which in 2022 stood at 80. Now, this is mainly driven by housing, followed by infrastructure, bridges, and landscaping or architecture furniture. This is very interesting if you compare that we are actually at the technology readiness level of 6 to 7, which indicates that it's in the prototype phase and that the prototype has been proven in the environment. Where if you have full maturity of the technology, that's typically only at a TRL level of 9, where it's commercially competitive in the environment. So taking it further, a recent study by Boss et al. Of projects in 8 countries, which includes Chile, China, Denmark, the UAE, USA, Germany, Italy, and the Netherlands, have found a few barriers that hinders the development of 3D concrete printing, of which the 2 main ones are the inclusion of steel reinforcement, as most of us know, as well as standardization. There's a lack of standardization, particularly for printed concrete structures. So this forces the industry to conform to the existing regulatory framework. And the consequence of that is that only 2 out of the 8 projects mentioned are fully load-bearing structures. So moving on to Stellenbosch. All 4 speakers that I will introduce just now are affiliated with Stellenbosch University, where we initially started the project in 2016 under the leadership of Professor van Zijl. And we developed the first 3D concrete printer in the Southern Hemisphere, followed by locally sourced materials. In 2019, we moved on to the structural mechanics. And in 2020, we scaled it to buildings. And the idea is to get this technology readiness level up to a 9 so that we can implement it competitively on a commercial level. So now it's my honor to introduce the speakers. We will have 2 speakers that focus on quality and then 2 on the productivity. So the first speaker takes a step back for perspective that as 3D concrete printing emerges in construction, it must also reduce the carbon footprint of concrete construction. So although it uses less material and produces less waste, it still has a higher paste content than conventional concrete. So per kilogram, it consumes more energy and has higher emissions. So Dr. Wipke de Villiers, she's a senior lecturer at Stellenbosch University, standing in for Professor John Babafemi that can unfortunately not make it today, will set the scene on the status of greening and circularity in concrete printing construction. The second speaker is currently a PhD student in 3D concrete printing at Stellenbosch University, Ruvimbo Munemo. And she's going to show us how interfaces are strengthened to address leakage, weakness, and sources of deterioration. The third speaker will start off with productivity, which is also currently a PhD student at Stellenbosch University, Mr. Bjorn, Haar, and he will present a case for off-site 3D concrete printing construction. And our last speaker, an alumni from Stellenbosch University, Dr. Marchant van Heever. He obtained his PhD in 2021 or 22, if I remember correctly. He's currently the Chief Technology Officer at Haar Technologies in Ireland, and he will present leveraging increased quality and productivity in residential construction. So with this, I present to you Dr. Wipke de Villiers to take us away on her presentation.
Thanks, Jacques. Okay, let me just get my screen shared. There we go. Okay, hello everybody. Yeah, as Jacques said, I'm Wipke de Villiers, standing in for a colleague of ours, John Babafemi. And so I'll just be giving a very broad overview of the concept of circular economy and how that relates to cement and concrete, and then also specifically to 3D printed concrete and what the opportunities are that we see there. And then I'll briefly touch on 3 case studies of experimental research work where we've been including construction and demolition waste in 3D printed concrete, which illustrates this concept of circularity specifically for 3D printed concrete. And so first off, up till now, we've, as a human race, have approached resources generally as infinite, meaning we extract what we need, we make what we need, we consume what we need, and we get rid of what we don't need anymore, with all of that going to waste. For the past few decades, recycling has obviously taken much more of a front seat, including downcycling and upcycling options. But even with these strategies, there's still a fair amount of waste that is generated at the end of life of the products. And so from a sustainability perspective, a circular economy approach is obviously the preferred option. And Wellenturf specifically defines a circular economy as an inclusive model that embeds the production consumption system into the biosphere and not as a separate system. There are many models out there for a circular economy, but this is one of the ones best suited specifically to the application of cement and concrete. And as you'll see in the diagram there, the blue arrows indicating the materials within the industrial process, with the green arrows then linking that back to the biosphere. And the intention being that we create a genuinely closed loop in the use of our materials, and then specifically in this case applied to the loops of cement and concrete. And as I think many of you may also be supporters of, there are numerous advantages to 3D printing in general, and then also specifically in the construction sector. Not to say that there aren't demerits to it, but the most often cited advantages are reduction in cost and in labor. With that also comes reduced risk to the labor force. And then on what we're interested in from a sustainability perspective is more efficient use of materials, and then also improved energy and efficiency of those materials. Less construction demolition waste. And then from a more functional perspective, this method is also more adaptable to functional architecture and to modular construction. If we're now looking at the material specifically that is involved in the circular loop of using 3D printed concrete, what we've got here is the relative the volume fractions of aggregate in maroon and the paste in gold, 4 different concrete types. So for conventional or for cast concrete, the first one, we're typically used to aggregate volumes of up to 70 or sometimes even 80%. So relatively small paste fraction there. For self-compacting concrete, the paste fraction needs to increase, and thereby the aggregate fraction then decreases to around 60%. And when we get to 3D printed concrete, the aggregate paste fraction is roughly half-half. It does vary depending on the application and the aggregate size and so on, but that's roughly the picture that we're looking at. And then for 3D printed geopolymer concrete specifically, that's the last column on the graph, that paste fraction increases all the way to 60%. I should just mention for geopolymer specifically that high paste content then obviously wouldn't have any clinker content. For 3D printed concrete, there are then kind of two angles of attack or two main aims that we would have from a sustainability perspective. The first would be to increase that aggregate fraction to as high as possible and to decrease that paste fraction, because the highest environmental impact comes from the cement content in the paste. And so we would want to have that as low as possible. And then also within the paste fraction, replace the cement with supplementary cementitious materials, and within the aggregate fraction also replace the natural aggregates that are used with recycled aggregate from within the industry. And so some of the opportunities that are available or that are being researched in 3D printed concrete in terms of the material specifically, on the binder side, a fair amount of research has gone into the use of our standard or conventional supplementary cementitious materials, but there's also emerging research on the use of unconventional supplementary cementitious materials. And then on the aggregate side, we would want to also replace as much of the natural aggregate with recycled materials, whether it's from construction or also from other industries. And so to move on to some of the research work that has been done here at Stellenbosch, I'll show you two case studies that were done at Stellenbosch, and then another one from elsewhere, where waste or construction demolition waste products have been used in 3D printed concrete, and what the findings of those have been so far. So the first study is by Oosthuizen, who included recycled waste plastic as the fine aggregate replacement in the 3D printed concrete. The plastic came from a local recycling facility here in Cape Town, and the material was supplied in particle sizes less than 1 millimeter and less than 5 millimeters. And so a number of different mixes were developed with these particle sizes, and then also the gradings of those mixes are shown here. And one of the things that we looked at was the buildability of these mixes with the recycled plastic content. The first top one, these are circular columns about 300 millimeter diameter. The top left, that's the reference mix with no recycled plastic content, which also achieved the highest print layer of 47 layers. So that was kind of the benchmark. But what was good to see was that the mixes with the finer particles, plastic particles of less than 1 millimeter, actually gave the best surface finish by far, which is also an important factor. And most of the mixes achieved a very good printability, with some of the mixes achieving as much as 42 and 43 layers, which is very close to the reference print of 47 layers. And then on the strength side, still here with the recycled plastic aggregate mixes. On the left, we've got the compressive strength, and on the right, the flexural strength. with the blue being cast specimens that were tested, and then the orange and the gray being the printed specimens for the two orthogonal directions, with D1 being the test direction parallel to the print layer, and then D3 orthogonal to the print layer. And as would be expected, the compressive strength for the cast specimens for the reference mix was generally was the highest. This would be expected, since the natural sand aggregate would also have a much higher stiffness than the recycled plastic aggregate. But overall, the specimens did achieve a structural strength, which would be sufficient to use. So that's encouraging to see. And then the second study that also incorporated waste materials here at Stellenbosch University was conducted by Heidi Christen, a PhD student. And what she did is she included recycled brick aggregate and replaced up to 64% of the aggregate in the 3D concrete print. And so she also used a combination of different brick aggregate sources, and in an attempt to reach the Fuller-Thompson grading with that aggregate. And so also conducted a number of different tests, including also the typical mechanical compression tests, with the sample on the left being used to then cut out samples for those tests. And the sample on the right is actually was the main purpose of the study. This was a printed building facade portion, where the recycled brick aggregate was also infused with phase change material to improve the thermal performance of the building facade. And then she conducted a number of thermal tests on that sample. But if we're just concentrating on the mechanical performance, again, as we would expect, the printed samples with the inclusion of recycled brick aggregate, or RBA, did show a reduction in strength, but again within limits that are still workable and usable for the application. And so overall, the findings of her study were that the RBA gives a very good surface finish, and is also very printable, which 390 millimeter high facade section indicated, and also the very low variation that she got in the compressive and tensile strength indicates a good repeatability of this kind of mix. The replacement of natural aggregate with 64% recycled brick aggregate did affect the strength, as we would expect, and as I mentioned, but up to levels that still make it a workable mixed design. And so the third study we're looking at, this was done by Pasupati and published very recently, just earlier this year, where they did a 3D print of geopolymer concrete with recycled brick aggregates in it as well. And they used I think an even mix for the precursor of fly ash and slag, and then the brick aggregate replaced the fly ash in proportions of 10%, 30%, and 50%. And so those different mixes were then studied. Compression at strengths tested in 3 different directions, and then also columns printed to investigate the buildability of this geopolymer concrete mix. And the buildability also presented very well. Again, looking or concentrating on the mechanical results. On the left, 7-day compressive strength, and on the right, 28-day compressive strength. And as we would expect, slightly different strengths for the different directions due to the nature of the additive manufacturing in layers, but overall still very encouraging results for these compressive strengths with the recycled brick aggregate included in the geopolymer. They also looked at the environmental impact, specifically quantifying the carbon dioxide emissions on the left and the embodied energy on the right for these geopolymer recycled brick aggregate mixes, and then comparing them to a more conventional OPC and slag mix for 3D printed concrete. So the OPC slag mixes are in green, and as you'll clearly see, the geopolymer RBA 3D printed mixes have a significantly less environmental impact. And so just in conclusion, the inclusion of construction demolition waste in 3D printed concrete is something that deserves a lot more attention and research. In fact, we are busy with a EU-funded research project with which we're wanting to replace 100% of the aggregate with construction and demolition waste. So that's something that we're working hard on. And then also aspects like developing lighter 3D printed structures to improve the thermal efficiency of the building envelopes, improving the interlayer bond strength, and then naturally also doing life cycle analyses of these types of mixes that we're developing to be able to actually quantify what the improvement is on the environmental impact. So that's it from my side. I'm now going to hand over to Munemo, and she'll be sharing a bit more on the interlayer strength.
Thank you, Bebka. I'm just going to share my screen now. Can you see it now?
Yes.
Looks good.
Okay, thank you. So good afternoon, everyone. I'm going to be talking about the technological improvements, specifically with regards to the interfaces for strength and durability. So the interfaces directly impact the interlayer bond strength in 3D printed concrete, and this refers to the strength of the bond between adjacent layers of concrete that are printed consecutively. And this is a very important factor as it directly impacts the structural integrity and durability of our printed object. So the several factors that need to be accounted for with regards to 3D printing are the limited material choices that you have to work with. Specifically, it has to be a cementitious mix. The size limitations, because your interlayer bond will be influenced the longer the print you're working with is. The resolution, which is essentially the dimensions and the geometry of your shape. The speed as well is an important consideration, as you want to ensure that your mix doesn't set prior to completing your full print path, which will then result in a reduced interlayer bond strength. And there's a lack of standardized techniques, as previously mentioned by Dr. Kruger. Then there's a limited understanding of the long-term durability of the printed object, and as such, it is important to continue to research this to confirm the long-term performance of our printed objects. These factors, these limitations directly impact directly as a result of the lack of fusion. And this lack of fusion of the filaments is one of the main challenges in ensuring that the printed object is completely the printed object is of the top quality that it can be. This occurs when the new layer does not sufficiently bond with the preceding layer, as you can see in the figures here, where there's a distinct separation in the two consecutive layers. This lack of fusion results in a reduction in the mechanical strength, which is the reduced structural integrity, with poor, weaker connections and compromising the overall structural performance. Then there's also an increased likelihood of cracking and can make the printed structure susceptible to more forms of damage especially with ingress of moisture into the printed object. There's also a poor surface finish, as you can see in this image, where there's visible seams and irregularities in the structure, which would be aesthetically disappointing and also affect the performance of the surface altogether. There's reduced durability, and the lack of the interlayer bond will increase the likelihood of the water penetration and damage over time, leading to reduced durability and the lifespan of the printed structure. The design considerations must be taken into account to ensure that the proper interlayer adhesion and overall durability of the 3D printed concrete objects are obtained. With regards to the process parameters, the layer height is an important consideration, as thin layers have weaker interlayer bonds, while thicker layers may have an increased risk of cracking or deformation. Therefore, there's an important balance that needs to be achieved with the layer thickness to ensure proper interlayer adhesion while maintaining the structural integrity of the structure. The object geometry is also very important, as complex shapes and geometries may need additional support and reinforcement. And currently, as previously mentioned, the incorporation of reinforcement is a very important consideration. Then with regards to the curing, with regards to the curing conditions, it is important to have proper curing conditions to achieve strong and durable 3D printed concrete. The temperature, the humidity, and the curing time have to be carefully controlled or carefully considered to ensure that proper hydration between the layers occurs and to achieve the proper strength. The environmental factors as well are important with regards to the interlayer bond strength, as the moisture that's available, the temperature changes, and the availability of the ambient conditions directly impact how much surface moisture is still available on the preceding layer prior to the placement of the next layer. Therefore, these must be considered these must be considered for the specific intended application and designed for while preparing for your print. The durability issues that can be anticipated are the moisture penetration, as well as cracking and deformation due to the ingress of moisture, and the material degradation is also greatly increased due to all these previously mentioned issues, with delamination and bonding being a result of the lack of fusion as well. The material used in 3D printed concrete may degrade due to the exposure to environmental conditions as well, and the weathering. Now, there have been a few methods that have been researched and implemented to improve the interlayer bond strength. The first one that I'll discuss now is surface preparation, in which the surface of the previous layer can be roughened or textured to create more surface area for the next layer to bond by sandblasting or acid etching. Researchers at ETH in Zurich have developed a method that uses sandblasting to improve the interlayer bond strength in 3D printed concrete. The technique involves roughening of the surface of the previously printed layer with the sandblasting nozzle to create a textured surface. There's also been pictured here, there's been research into using a comb to just texture the previous layer. Cobard has developed a process that involves using a high pressure water jet as well to clean the surface of the previously printed layer and create a slightly roughened surface. The second technique to improve interlayer adhesion is topological interlocking. This technique involves designing the printed structure with interlocking geometries that improve the bond strength between the layers. Currently at Stellenbosch, one of the other PhD students has been doing research into finding the appropriate geometries and the geometry measurements that will improve the interlayer bond strength sufficiently. Topological interlocking has been determined to increase IBS, the interlayer bond strength, by approximately 25 to 30% from just the smoother surfaces. Another method that has been investigated is the use of heat. Applying heat to the previous layer can improve the bond strength between the layers, and this can be done using methods such as hot air or infrared heating. Researchers at the University of Southern California have developed a method that uses infrared heating to improve the interlayer adhesion, while Winsun, a Chinese construction company, have used a printing process that involves extruding a mixture of recycled concrete through a nozzle and then curing that material with heat. Currently, we're also at Stellenbosch, we're researching the use of steam on the interlayer to improve that the interlayer bond strength. Another method is bonding agents, and you can see from the image how those would be incorporated. Bonding agents such as epoxy or acrylic resins can be used to improve the interlayer bond strength. These agents are applied to the surface of the previous layer before the placement of the next layer, with researchers developing a method that uses acrylic bonding agents to improve that interlayer bond strength in the 3D printed concrete. Zijl Construction, a Dutch 3D company, applies an epoxy bonding agent to the surface of the previously printed layer, and have managed to achieve 30% improvement in their interlayer bond strength. The final method that I'll be discussing today is the application of pressure to the previous layer. The application of pressure is used by simply vibrating or pressing the newer layer into the substrate. This has been found to improve the interlayer bond strength by approximately 20% from the smoother surfaces. University of California, Berkeley developed a 3D printing technique that uses a robotic arm to apply pressure to the material during the printing process. The robotic arm applies pressure to the material as it is extruded through the nozzle, helping to compact the material and improve the interlayer bond strength. Finally, and in conclusion, one of the most important considerations with regards to these methods is how easily they are applied to the apply to the technique and the technology, because one of the main reasons why 3D printed concrete is an important consideration is how much faster it will improve construction times and efficiency and the quality control. And these methods need to also directly need to be optimized to ensure that they do not diminish the advantages that have been identified for 3D printing. And as you can see from this graph, proper consideration of the design factors is essential to ensure that the method that has been selected sufficiently improves the interlayer bond strength while being easily applied into the technology without completely taking away the previously considered advantages. So as interlayer adhesion is a crucial factor in achieving the desired strength, durability, and performance of 3D printed concrete. Improving it requires a multifaceted approach, which will include optimizing the print parameters, and the surface preparation, and using the bonding agents. Industry players and researchers have made significant progress in this field, but there's still a long way to go to ensure that the 3D printed concrete structures are meeting the desired performance requirements and durability needs. Thank you so much for your time. I will be handing over to Bjorn now.
Thank you, Ru. I'll share my screen. Hello, everyone. Good afternoon. I'm excited for the presentation. So the previous two presenters, as you saw, focused on the material of 3D concrete printing, and they went into the quality there. Now we're shifting over to construction approaches and types of structures that are being built. And just a reminder, the question being asked, it is 3D concrete printing improving the productivity and quality of construction? And I would like to propose that we need to look at the types of structures and at the construction approach that is selected almost individually on a case-by-case basis, and look at the qualities thereof. So I will be focusing a lot on offsite 3D concrete printing. And yeah, let's go ahead. Let me start off by explaining quickly. Most of you would be able to, would know this by now, but the offsite approach for 3D concrete printing would involve preparing your concrete at a facility, taking it to a factory, prefabricating your element with your printer that is already set up there, transporting your elements to the construction site, and then assembling your elements on site. Then with an on-site approach, the main difference being after you've prepared your concrete, you transport it directly to your construction site where you install your printer for each project. Then you pump your concrete for your printer and then monolithically construct your structure. Then you have to deassemble your printer and move it to the next construction site. So deciding between these two approaches would probably take place on a project basis, and what your client needs, what type of structure, how large your structure needs to be, location of your structure, is it too far from a factory, and so forth. So it's, yeah. Now I'd like to look at two types of structures that could be used or are being used, that are being constructed using 3D concrete printing. The first one is what so far has been the main target market for 3D concrete printing, and that is your low to medium rise load bearing structures. What I mean by that is structures where the walls carry the load of the building. And a study that was performed in 2021 found that for a single story 40 square meter house, 3D concrete printing performed greater in cost and schedule performance for the project. This was a theoretical study that looked at the whole construction process. And the study compared both on-site and off-site 3D concrete printing, and both on-site and off-site conventional concrete construction, and for a round and a rectangular house. And as you can see, the on-site 3D concrete printing performed the best, followed by the off-site 3D concrete printing. And so based on studies like this and from real world experience, we can see that there is a good possibility that 3D concrete printing can already improve the cost and schedule performance of construction projects. And our next presenter, Marchant, will go into, Dr. van den Heever, will go into more detail into these kind of structures. So what about another kind of structure? The second one I'll be talking about is what about framed structures, 3D concrete printing of frame structures. Unfortunately, yet we don't have any examples of structures that have been built with this. So we don't know if it would be more productive or the quality would increase. But at Stellenbosch, we are investigating a solution and developing a solution for a structural frame system using 3D concrete printing. But this would be using an off-site construction approach, where a lot of the load-bearing structures used an on-site 3D concrete printing process. Several reasons for that, but just at first glance, there seems to be a few promising benefits of taking the off-site approach. instead of the on-site approach. For instance, in terms of quality, you're ensuring a controlled environment in your factory where your elements can have high quality. The interlayer bond strength, you can use, you can control your environment to ensure that's as strong as possible. And another one in terms of quality is your building size is not limited by the size of your printer. You can print your elements and then theoretically keep going in height and size of your structure. And then in terms of productivity, you remove the step of needing to assemble your printer at every construction site. And obviously there might be some downsides to productivity and quality in using an offsite approach, but just at a first glance, it's looking promising. So before we started developing the structural frame, we decided that we need to understand how an offsite construction process would work with 3D concrete printing, and what are the challenges and what we need to look out for. So we conducted a systematic literature review seeking to answer the following questions. What can hinder offsite 3D concrete printing? Who is involved in the process? And how can we increase the success of these offsite building systems, 3D concrete printing building systems? This led us to a list of driver barriers for 3D concrete printing and offsite construction, which we got from literature, and we got a list of stakeholders, the people involved in this construction approach, and we identified or derived a list of specific targeted actions for stakeholders to increase the success of these building systems. So if we look at the driver barriers that we identified from literature, there were 9 of them for 3D concrete printing. And the topics that were discussed the most in literature, as you can see, were environmental performance, fresh state and hardened state material requirements, the reinforcement of 3D concrete printing. And this gives us an idea of what we need to focus on when developing these building systems. And then looking at offsite construction, we identified 13 topics, 13 driver barrier topics. And there we found that project delivery and logistics, cost and schedule performance, labor and design were the most discussed topics, which gives looking more at the construction process than the technology. And this gives us a broader view of what we need to consider when developing a building system with offsite 3D concrete printing. After we identified these driver barriers, we asked the question, so who is involved? Who are the stakeholders of offsite 3D concrete printing? Who can influence these building systems to make them successful, to make them more productive and ensure quality of construction? And there were 15 of them from literature. 2 of them I would like to highlight that are probably unique to 3D concrete printing is that you'll have specialized component manufacturers fabricating your beams and your columns and your walls and your building elements. And then you have specialized fabrication equipment suppliers, the companies developing your printers and your pumps and your concrete equipment for 3D concrete printing. And then one more stakeholder that I would like to highlight is, since most of the people attending this webinar, or a large number of them, would probably be engineers or architects, you would fall into the category of the designers. And your role in enabling successful offsite 3D concrete printing building systems is critical. And you might be asking, how can you do this? So we then, from the lists of driver barrier topics, we derived 34 different actions, targeted actions for these stakeholders. And they were divided into 4 levels. We have your building system level actions, we have your project level, your organizational level, and your industry level actions. And since as you can see, these 4 different levels, it indicates that just having a functional and well-working building system is not it is not enough to ensure that it would be successful. We need the whole industry to get involved and organizations to get involved to improve the productivity and quality of construction using this technology. So for the designers, out of these goals, 47% of them require the designers to get involved. So here are some examples of these actions. We need to develop design guidelines and technical standards for offsite 3D concrete printing. We need to develop and implement business operations with integrated digital technologies to improve productivity. We need to optimize material usage in building components. And we need to develop 3D concrete printing reinforcing strategies that provide ductile behavior of elements. So designers, you are a critical stakeholder and you have the opportunity to influence offsite 3D concrete printing. And if you are one of the other stakeholders, there are plenty of other targeted actions available to get involved in. So in summary, the findings from our presentation: 3D concrete printing can already increase the construction productivity of load-bearing structures. Offsite 3D concrete printing building systems for frame structures show promise, but still need to be developed and trialed. Success of offsite 3D concrete printing is not exclusively dependent on the building system performance. And then finally, the designers are the critical stakeholders in offsite 3D concrete printing. In summary, here at Stellenbosch University, we are excited for the further development of these building systems, and we're optimistic that they can improve the productivity and quality of the construction industry. And on that note, I'm going to hand over to Marchant.
Thanks very much, Bjorn. Very interesting presentation. I think let me just quickly share my screen. Let me just pop this into presentation mode. Should start now. Just skip there by accident. Yeah, thanks very much for the introduction, Bjorn, and then to the other presenters doing a very good job of explaining some of the technical aspects related to quality, and then Bjorn giving a very nice overview of the advantages and the key considerations in terms of stakeholders, making a very compelling argument for offsite construction. Today, I'll be speaking about leveraging increased quality and productivity for residential construction. As Jacques introduced, I am a research fellow at Stellenbosch University, but I'm also the CTO at Haar Technology. So I'm speaking from both an academic and sort of a commercial perspective today. Firstly, to give a bit of context to the offsite manufacturing or the on-site manufacturing process. As Bjorn said, the designers are very key because we have a building that we want to design, and that building is already designed within a digital process. Your architect designs digitally, your engineers design the stability of the structure on digital programs and on digital platforms. Your planners, your quantity surveyors and your contractors all plan and cost your project digitally. And now what we do is we extend this digital process where we slice this building that we designed, our digital model, we generate G code, and we then link that up with various raw materials to then directly print the structure on site. So in terms of our raw materials, we've got different phases. And in general terms, we have three main phases in this process. The first be sort of your material delivery phase, then you've got your pumping phase, and then you've got your printing phase. In your material production or your material delivery phase, the open time of your material is really important, because you need a material that remains workable for a sufficient amount of time to allow you to pump that. When we look at pumping, obviously the pumping pressure is really important, and we can't have segregation. You need the right slump flow, so we generally use some plasticizers there to ensure that we can retain sufficient levels of workability. Obviously then you pump your material, and then that material needs to enter the printing phase, where the first sort of sub phase that you reach is your extrudability, which generally just is a term that we use to say how well can you extrude this material, and we need a continuous rectangular or rounded filament that you deposit. But this then requires the material to stiffen upon deposition, which is generally speaking quite competing material requirements, from a fairly plastic material to a material that then sort of has to present viscoelastic properties. We generally leverage a stiffener for that purpose, but then we have to stack these layers on top of each other. So that's where we enter the buildability phase. We need to ensure that we don't have fresh state failure. A very important parameter is your layer time. So your layer time is the time that it takes to deposit one sequential layer, sort of if you look at in plan on the structure, to do one loop around this entire structure. But this is very important for one, the building performance that you require. So at what rate are you stacking material? But two, it's very important for your interlayer bond strength, which Rue went through in quite a bit of depth. Obviously, your concrete temperature and your accelerators are very important there in terms of the hydration kinetics involved in your material. We also then look at durability and cracking. We then look at the structural integrity, because obviously we want to use this printed material in a structural manner. So we look at the compression capacity of the material, we look at the tension of the interlayer, and this is greatly affected by environmental conditions and your accelerators that you use to gain building performance. But then it's very, very important to also consider cost, and this layer time, buildability, and the structural performance that you need are key drivers for the productivity of the structure and of this construction methodology. So just looking at the benefits, again, we've been through these, so I'm not going to go into them in too much detail. And today I'll be focusing on quality and speed. In terms of quality, using really high performing material. So you've got you've got a lot of compressive capacity, but you've also got a very accurate and consistent placement of material. So what this means is that once you've signed off your building, once the construction model has been signed off, the contractors and the various subcontractors involved in the project know that their specific components are actually going to fit. And I'll go into this in a bit more detail. In terms of speed, we've been able to achieve very rapid building rates, about 30 square meters of wall area per hour, printing at about 250 mils per second. I'll go into that in more detail, but what that means is our construction time frame can be reduced by 50%. So essentially we can build twice as fast. And this is through leveraging the integration of prefabricated components, which I'll go into a bit more detail in. In terms of how we can leverage productivity and how we can maximize productivity, we considered a few ways. So one of the most obvious ways to think is to print faster, to physically move the nozzle faster. But this has a few implications in terms of, say, the inertia of the print head, the stability of the print, and sort of the mechanical strain that you place on your equipment. And what we realized, if you look at this graph that I have, that increasing your layer height, so the physical geometry of the layer, is one of the most efficient ways to increase your production rate in terms of square meters per hour. If you look there at a 10 mil layer height, a 30 mil layer height, and a 50 mil layer height, which we typically use for large scale in situ structures, printing at 250 mils per second, we can get 45 square meters of wall area per hour. Now, what's very interesting about this is with larger layer geometries, we can scale up the size of our aggregates that we use. And I think coming back to Vibke's initial presentation on paste volume, having larger aggregates means you have a smaller surface area, so you physically need less paste to coat these particles. So that improves our sustainability as well. What this also means is we move towards more standard types of concrete. So we're using anything up to about 10 mil. We've used slightly larger as well. And because we're using standard concrete, it means we're moving towards more standardized supply chains. And that very importantly means we're moving into a lot more competitive pricing on our materials. I think as Jacques quite rightfully mentioned, that's going to be very important to reach TRL 9 to actually have, commercial competitiveness within the environment that the technology is employed. So if we just look at the system in terms of these more, traditional supply chains that we have, about 99% of our material by mass is traditional normal concrete, cement, aggregates, and water. And then a small percentage is a few different sets of additives. We dispense these through 3 respective material solutions. And as you can see, you've got a ready mix truck there, which we all understand. A dry batch silo, which is traditionally used in industry as well, or you can use a mobile batch plant, which means we actually get very close to the normal procedures that we use on the construction site. So here I just have a little video as an overview of some of the testing that we did with Cemex and Cobalt. Where we use a traditional ready-mix truck. As you can see, that concrete doesn't look very different from traditional concrete. It's then dispensed directly into the concrete piston pump, which again is very standard. Materials, as you can see there, for our initial testing, we had to get the setting of the material right. And this is before we accelerated the material. Once we add the accelerators and stiffener, you can start seeing that we are able to get sufficient building capacity. And then once we dialed out the parameters, we get very consistent and reliable printing quality on a very large scale. So what's important here is to link up the actual setting time of the material with your layer time, but to ensure that you have the vertical gain rate that you require to maximize your productivity. Now, just looking at 2 case studies. First one is in Beckham in Germany, where they printed 2-story building with 160 square meters. The total printing time was 36 days. And then you can see that they took 28 days for the ground floor. But the reason is they had to wait 14 days for the in situ concrete slab to get propped, the steel to be fixed, cast in situ, cure, and then they could strip and carry on with the second floor once they have a working platform. It then took 8 days for the second story, and this is a building that comprises load-bearing and non-load-bearing components. It's also fully permitted, which is very important. The second one is another building printed in Germany by the Perry Group. This time 3 stories, 380 square meters. But it was printed in 21 days, only 7 days per story. And the reason it being that they used a timber flooring system, prefab timber flooring system, which greatly allowed them to accelerate the overall construction procedure. So what I'm hinting towards here is that yes, 3D printing is fast, but fast buildings don't constitute, well, fast walls don't constitute fast buildings. So it's very important to consider the ancillary construction components and leverage this quality, sort of the accuracy of your placement to achieve productivity on the building site. So what I have over here is sort of a methodology that we use at HTL where we leverage prefabricated components. So what you'll see, you'll excavate and have your damp-proof membranes. We then use a prefab insulated floor slab, print the skirt of the building, drop in the insulation to ensure that we don't have any thermal bridging. And we print the ground floor on sort of the south block, install our prefab lintels, prefab partitioning, and prefab flooring system. As you'll see, we alternate between the two blocks. So what that allows us is access to install our prefabricated components whilst we are printing on the alternating block. Through this sequence, we basically eliminate task dependency on the construction program. So we're fitting and installing prefabricated elements that we know that will fit whilst we're gaining height on the opposing side of the building. So within a 12-day time frame, we've already taken away the machine. You then install prefabricated roof trusses. That can be timber or light gauge steel or whatever system you want to use. Again, a prefabricated circulation core, cladding, and you've got your structure. So in terms of productivity, as Bjorn said, we definitely are at the point where this technology adds to productivity in the construction market. Finally, just to summarize on my presentation, it's very important to leverage precision and sort of promote a hybrid construction procedure through the integration of prefabricated elements. Create an in situ superstructure. So the largest portion of the building element, the heavy concrete walls, we fabricate directly on site with a lot of precision. And then we rely on offsite ancillary construction components, which we can reliably insert into the overall superstructure to get a sealed envelope as fast as possible, and thereby, leverage the quality and precision and promote productivity. Just finally, so in terms of productivity, construction block, traditional cavity blocks, about 2.5 square meters per hour. 3DCP at a 50% contingency is about 15 square meters an hour. So that's 600% faster. We're about 29% cheaper. And we're not limited to the traditional vertical gain rate that block is of 1.5 meters a day. We can go up to 2.8 meters a day due to this superior material performance that we leverage. Thank you very much. And I'll now hand over to Jacques again to take the questions.
Thank you very much to all my colleagues for your excellent presentations and sharing your valuable research and as well as industry findings with all of the participants today. So to get back to the initial question, is 3D concrete printing increasing construction productivity and quality? Well, the answer is perhaps in some instances, yes, and in others, not yet. So as we've seen that there's a high paste content currently with 3D printed mortars, less so with the concretes where actual large aggregates are included. So that's one aspect that needs to be focused on, but we are doing research as Dr. de Villiers showed us, so that you can include SCMs and even limestone calcine clays. And then also there's other barriers, for instance, the interlayer bond strength, as we have seen by Revimbo, but obviously there's a lot of options to improve that. So I want to open the Q&As. And I'm going to invite my colleagues to switch on the cameras, and then I will try to answer some of the questions. So the first question was by Ying Chia, and he asked, is there any limitation in terms of the height of structure one can achieve with 3DCP? What is the highest building constructed using 3DCP? So I think the best to answer is Dr. van Heever. Maybe you can just give us a brief answer on this, and maybe even include limitations, whether it's from a material perspective or even a machine perspective.
Yeah, thanks very much, Jacques. So I think the question is twofold. So the first one, I'd say in terms of sort of a technical limitation, no, there's no technical limitation to the height of a building that you can, the overall height of a building that you can print. However, there is a limitation to the height that you can print within a certain amount of time, and that is a material constraint. So your material has a physical building performance, so you can gain a certain height during a certain period. And that's linked to your structuration rate. Now, obviously, you can have infinite amount of sequential procedures where you print sort of sections and then another section and another section. So that would more be sort of an equipment constraint. So I know Cobard, the tallest building, so to sort of get to the second portion of the question, the tallest building at the moment is 9.1 meters, and that was executed at the end of last year in the UAE. And then I know GE, General Electric, working with Cobard again, and Holcim have printed a 10-meter wind turbine, but they've also now built a 25 by 25 by 25 meter machine. They call it the Bod XL, which obviously is designed to print wind turbines up to 25 meters high. So I think it's just in terms of your practical limitations in terms of your equipment and the capital investment required, to facilitate certain sizes of equipment. But yeah, there isn't a limit necessarily to the height that you can print at.
So essentially, it's just where the TRL level is currently at 6 to 7, that once we get to a TRL level of 9, where it's commercially viable, that we can print very tall structures.
Exactly. I think,
yeah,
and one more item to add is obviously if you're doing an unreinforced structure, like a compression only structure, codes only allow you to go up to 3 stories. So there isn't really a point to go higher. If you're going for a frame sort of construction methodology that Bjorn presented, obviously that lends itself more to commercial type buildings where you'd go, more higher rising, more dense type structures. So it depends a lot about the certain application that you have in mind.
Okay. Then we have a question from anonymous attendee, and it's a very important question that sometimes we tend to forget as engineers focusing on the hard skill side. And this is, have any of the printed bits been tested for sound absorption, thermal, and possible scrubbing of emissions? So we have done some thermal research by Heidi Christen, and I invite Dr. de Villiers to maybe share some more on her research.
Thanks, Jacques. Yeah, so I mean, at the end of the day, even though it's printed, it is still concrete. So on the material side, it is basically still a concrete material. But the big advantage of 3D printed concrete that we need to leverage in terms of thermal is the complex geometry that you can print. And so, as also indicated earlier, PhD student Heidi Christen, she did thermal tests on a 3D printed facade. That specifically was with the inclusion of phase change materials included in the recycled brick aggregate, which performed really well, but that's specifically now on the inclusion with PCM. We also had a master's student, Hanley Murray, who did thermal analyses on 3D printed facade sections, where she looked at optimizing the geometry of the section for an optimal thermal performance. And so there's a lot that one can do, whether it's with the inclusion of PCM, whether it's optimizing the geometry and so on with the thermal performance. With regards to sound absorption, I'm personally not aware, but yeah, again, that's certainly something that can be looked into.
And maybe just as a summary, if you have to compare a normal, let's say a double skinned wall, brick wall, to a 3D printed wall that has a cavity without any recycled brick aggregates, did you find that it has better thermal insulation?
It does. What one does need to just be careful of, so with a kind of cavity wall, compared to a printed section where you would typically kind of have interconnected bits between the two outer layers is, or one thing that one must just be careful of is the thermal bridging. When that you don't get too fancy with your geometries, but overall it would give a better performance. Yes.
Okay, good. Then another anonymous attendee asks, how can controlled environmental conditions improve the bond strength? So the expert, Roo.
Thanks, Jacques. So due to the layer-wise technique of 3D concrete printing, when the substrate is left exposed to the environment prior to the placement of the next layer, depending on the pass time, that surface that's exposed is subject to whatever environmental conditions that that are available while you print. So higher, drier, windier conditions will lead to faster drying of your surface. So this is even before your concrete has stiffened or hardened. It's just the drying out of the surface of your printed filament. And if the drier it is, the lower the chances of good interlayer bonding and hydration, because there is less moisture overall. So controlling these environmental conditions will reduce the chances of your surface drying out and increases that moisture available for your hydration to just improve that interlayer bond.
Okay, so are there any ideas how we can facilitate a better environment for printing? So how do we, prevent the environment's influence on the interlayer bond?
That is a very important question to consider, because you would want to have on-site printing, not just factory printing and all that. So an option would be having covered printing sites. So rather than just allowing free movement of wind in your site, you'd probably want to build a temporary controlled region. And with regards to the temperatures and just the other ambient conditions, that now goes back to the material that you've prepared and making sure that your material is able to withstand that length of your pass time. So it goes back again to your design considerations to make sure that prior to even starting your print, you've made sure that your mixture is able to withstand that pass time that you want to have.
Yeah. Okay. So you can include it in the design process as well to accommodate for that environment. Okay.
Yeah.
Thank you, Roo. So here's a question I'm going to direct to Bjorn from Amrinder Singh. Please explain the 3D printing subjected to seismic forces, any specific parameters and methodology that has been developed. And then as a second follow-up question, how can it be beneficial than hollow block structures?
Thanks, Jacques. In terms of seismic forces, I'm unaware of any research that's been done in that for 3D printed structures. And yeah, I think with seismic and concrete, your reinforcement is is important, getting enough confinement. So that is probably a very important ongoing research to look at. And especially when we start, if we start using 3D concrete printing for 3 stories and up, as Marchant was saying, and you start looking at a frame system. But I think there has been some research on some shear walls using 3D concrete printing. So it is, as we look into reinforcing 3D concrete printing, this is definitely an area of research. And the same part was beneficial than hollow block structures.
Correct.
On replacing it, some people are saying that 3D concrete printing won't necessarily replace these kind of structures, but would be beneficial in certain circumstances. It would be another tool to use in our construction basket. So how it could be more beneficial, I think Marchant touched on a lot. You can definitely improve your construction speeds and yeah, we spoke, there's all the benefits of 3D concrete printing. You could look into your thermal performance with your cavities and your complex geometries, as Dr. de Villiers was saying. So you can definitely leverage the advantages of 3D concrete printing to improve the building's performance compared to when using hollow blocks. Yeah, Jacques, I don't know if you want to add any other.
Yeah, maybe as a follow-up from our side to this, do you think there's a possibility of using these two technologies in tandem? For instance, where you have this frame structure that you've developed where there's reinforcing inside, and then still using the hollow blocks, for instance, for lighter walls, where it might be even lighter than printed walls.
Yeah, I think that sounds like a good idea. Also using alternative materials. Maybe concrete is not the best material in your local environment, but you would need it for your structure. There's a lot of innovative building materials being tried and tested, and some that work in a country that has a lot of timber. Maybe you want non-structural timber facades, but you want your structure out of concrete. So, and then hollow blocks. I know Stellenbosch is also doing some research in hempcrete, which is looking promising on the sustainability side once again. But the hempcrete concrete blocks, the structural performance of them it's not yet sufficient to be a load bearing wall. So yes, in tandem, I think that would be a good solution, and hopefully we can work into. Yeah.
Okay, interesting. Another question on rebar reinforcing, which is really one of the main barriers with printing. Can you show how do you put the reinforcement into the cast in situ 3D printed concrete load-bearing walls? Wouldn't the reinforcement clash with the nozzle? Marchant, do you perhaps have anything on that you can share with us? How you guys do about that?
Absolutely. So obviously reinforcement, we use it bidirectionally in most cases. So you've got some lateral resisting reinforcement, and then you've got your sort of your vertical or your reinforcement for bending resistance and shear resistance. In terms of lateral support or reinforcement, you entrain those directly into the layer. So we quite often use fiber in our mixtures to provide ductility, increase the toughness, but then also improve the tensile capacity. It depends on the dosage of the fibers that you use, but you can also, so when I was doing my PhD, I directly entrained pieces of rebar and printed over them. With this pressure of the layer squeezing over the rebar, we really get good bond. So you get a good bond with your rebar, which is obviously very important. In terms of your vertical rebars, what we generally do is we'll have starter bars that come out of your slab, as you would for traditional cast in place column, where you'd have your starter bars, fix your cage, box it up, and then pour in situ. Now the process just switches around sort of in a way where you'd have your starter bars that are high enough to give sufficient lap length, but not high enough, low enough, essentially, so that it doesn't clash with your nozzle. So you print around it, you then drop in your cage, and then you pour in situ. So you print permanent formwork in essence. And another solution, if you don't want to go for the starter bars, is having a coupling. So you basically have a coupling that protrudes from your base with a screw tip, and then you screw your rebar into it. From an installation and fixing perspective, it's a little bit more tedious because you quite often have about 2.8 or 3 meter lengths, and you got a torch, and then you have to find that little coupling and screw your bar in. So we generally prefer the starter bar that's lapped, which is quite a traditional method as well. But both can be achieved as required.
So you're pointing towards that we should look at alternative methods of reinforcing 3D concrete printed structures and not necessarily just go to conventional reinforcement.
I think there's a case to be made for sticking with the conventional tried, tested, codified manners, because that's something that designers and your authorities understand. But then I also think there's a very strong case to be made that this is new technology that requires new solutions, and we should, quite rightly generate new solutions to accommodate the most efficient, productive use of this technology. So I think it's twofold. There's a certain time which you'd lean on traditional methods, but there's a certain time that you would look to innovate in this space. And we have seen, I think there's about 13 or 14 different strategies that have been sort of tabled in research lately, anything from, sort of wire entrainment to fiber entrainment to nailing to, I can't even think of all the different types of reinforcing. There's loads of them. And I think that speaks for the innovation and the drive that this technology has. But, at the end of the day, you're going for a science certifier route. It's the engineer that has to be comfortable with it at the end of the day, because they've got the most liability for the stability of that structure. So it's going to be, again, I think it touches on what Bjorn presented, engaging with your stakeholders and sort of finding the most practical solution for the specific requirements.
Another very important question that I noticed in the Q&A, and this is, we don't really see this in all the videos that we see on YouTube and on social media, but Jasper Schilder asks, need on-site printing post-treatment of surface? So essentially, do we need curing for 3D printed structures? Typically, we don't see it. We just see the structures and, it's ready to live in them and so on. So how important is that? I can maybe direct this to Wipke.
Yeah, so practically there are obviously always difficulties with curing on site. And as you said, we don't really see it. If for extreme environmental conditions, when it's very hot and very windy, I imagine you would have to take some measures to protect against that. But yeah, I mean, please add in from your side, Jacques. But I think from a practical perspective, we would want to try and avoid the necessity as far as possible.
Yeah, so we have actually done some research on using curing agents from a previous student, Gerius Mulich, that's now at Cobot. Investigating if you can use, for instance, super absorbent polymers, which retains water and it delays it over a longer time, or even just using normal application of a chemical admixture, that you can buy from a supplier. Because, I mean, it's not possible to wrap the building in some plastic wrap or any of the other bonding methods, or even using sand, for instance, in some instances. So yeah, we have to be innovative, but I would like to hear from Marchant, how do you approach it on site? Is it an automated process? Do you have to do some post-processing where you actually have to walk around the building and maybe spray it with some liquid or chemical? How do you guys go about it?
Yeah. So the way that we approach it, so we've actually got 3 different methods. So whilst we're printing about 500 mils down, we spray a curing agent, which it's like a concrete densifier, basically, just to ensure that you sort of lock the material in and retain the moisture that's within the leaf. But then in terms of evaporation and plastic shrinkage cracking, your top layer, your last layer, the exposed area relative to the volume is the highest. So you typically get cracking on your top 2 layers. So what we do is we throw burlap or sort of like Hessian tarps over it, very similar to what you do when you're curing a traditional concrete slab. And we then have on the bottom of our x-axis of our machines, we have a misting system, which we run then for a certain period of time. And with the 2 leaves, we spray some water on the inside of the leaf as well. And that means when the concrete's curing, it generates humidity. And this humidity sort of serves as a curing methodology. So, but most important is protect those top few layers just after you stop printing to ensure that you don't get, because the crack will then propagate from the top of your last layer into the subsequent substrate layers. So most important is to protect those last few layers. And that's just the Hessian top, sticking to what we know.
And the bottom layers, do you just leave them, or do you also
look?
some
So
process there?
we've got the curing agent on the external surface that's exposed, but we don't rack the bottom layers, no. So
Okay.
and then just the moisture from spraying with the misting system generally helps
Okay.
sufficiently for that.
Yeah. So that question is answered. It's definitely necessary, and there are methods to address that. So here's another very interesting question from Michael Montefalcon. How do you address the balancing stability and flow? 3D concrete printing needs to exist in two different states, which have completely opposite properties. So this is a question we get quite often. The long answer is thixotropy, where you actually rely on a material's rheological performance, which it's different than conventionally cast concrete. But there's also a easy solution on site, and Marchant actually showed it in his presentation, where they add mixtures at the nozzle. For maybe Bjorn can explain to us what process he had to go through, where he had to design a column and print a column, where there's limitations to either of these. So if you go with thixotropy, you can only print as Haar. Then you need to go to an admixture or a chemical accelerator to get it faster. So Bjorn, maybe you can just take us through that process.
Yes, they say you learn from your failures. So we were very limited in so when you printing a something with a small path length, so you gaining speed rapidly. What we attempted to do, or gaining height rapidly. So what we attempted to do was incorporate a rapid, a bit more of not a rapid setting cement, but a faster setting cement. On the one side to improve your thixotropic parameters. So it would still be pumpable coming out of the concrete mixer, but then we were hoping it would set fast enough that you could get you could print high and get good buildability. And there was quite a limitation with that. We were using CSA cement, but then so now. We ended up reaching, it's probably not about 500 millimeters. And now we have to move over to your second option, which is to use the accelerator, which doesn't rely on the thixotropic parameters. And you, at the nozzle, at the print head, you inject an accelerator, and then your concrete mix sets very rapidly. But once again, now you need to get your balance. If you're printing a wall, or a long wall, you need to get your dosage right, because if your concrete sets too quickly, your interlayer bond strength is going to be weak. So it depends on your, what structure or element you want to print. So for our application of when we print a column, we're going to have to use an accelerator. For elements with a longer print path, you can come right by using the thixotropic parameters of your concrete.
So essentially, if you can summarize it, that if you print fast vertically, you need an accelerator. But if you print slower vertically, so longer print paths, for instance, a house, you could perhaps get away without using an accelerator.
Yes, I would say that. And you would need to weigh up, do you want to use an accelerator in terms of cost, sustainability? That's considerations you need to take into account.
Then There's another question by anonymous attendee. Texturing of the surface increases the bond strength in which direction? So we'll ask the expert Roo to tell us maybe a bit more about that it's not just in the IBS, but also in other directions.
Yes, so when you've done surface texturing, it's essentially, it improves the bond in a mechanical sense, because there's now a form of just interlocking between the newly placed layer and the previous one. So even if you check in your D1 direction, which is parallel to, which is if you're testing parallel to the print layer, you still will you'll notice that because of that friction that it causes, there's an improvement in the strength of the concrete. So it's not just in the interlayer direction, it's also in the D1 direction, and that's just generally what you want, because that it improves the overall performance of your printed object.
There's a follow-up question by the same person, I believe, on that it seems there's conflicting you know, there's a conflict between the chemical and the physical side of the bonding. Do you believe there's a possibility of perhaps, you know, that they work better in tandem, even to get a stronger interlayer bond strength than just using them separately?
I actually believe that it's the perfect method would incorporate both a chemical improvement and a physical bonding aspect, because you want to be able to encourage the hydration within that mechanical bonding that you've encouraged. So it's not just one or the other. The perfect method would incorporate both of them, because if we look at topological interlocking, one of the issues that was observed a lot of the time was there would be a little hole or space that develops in some of the edges or the corners. So if you had a chemical aspect added into that situation as well, which would encourage whether it's additional bonding or just hydration in that space, it would then have an overall better performance rather than creating voids in that in the shapes of the topological interlocking.
Okay, sounds good. We look forward to your results on that soon.
Sure.
Okay, there's maybe a question, the last question that I'm going to pose from the floor and I'm going to make it open to all the presenters, and anybody can really choose to answer, because I have no idea on this yet. But has there been any research regarding the inoperability of 3D concrete printing with other digital tools, such as the digital twin, to provide inside data on the actual construction performance of the building during operational phases? I think, Wipke, this one seems to suit you perfectly.
To be honest, I'm not sure I'm in a position to answer that.
Not yet.
Not yet. We've been, one of our upcoming projects is to kind of connect the flow from BIM models all the way through to then printing elements based on that model, and making that a far more automated process. And a natural progression from that would then be to have a digital twin of the actual printed elements as well then. But yeah, in short, I am not aware of research that's been done on that specifically at this point.
Okay, and if you have to give a time frame, I mean, you know, you've just started this project at Stellenbosch also into the recycle BIM. How far in the future do you see it actually being the norm as forming part of the printing industry?
I mean, not just in construction, but I mean in all in sectors right across. It's developing so quickly that I think once we've got once we move into that direction, I don't think it would take much time to actually then move into that as well. It's there's a lot of supporting development has gone on in other sectors and in other industries, that I think it shouldn't be too challenging to translate that to 3D concrete printing specifically then, yeah.
Very exciting. All right, ladies and gentlemen, it seems our time is up. So I want to once again thank all of our speakers and my co-colleagues for the excellent presentations on printing. I think we have answered the question of today's title. And yes, thank you all for attending. We hope you enjoyed it and enjoy the weekend. Bye-bye.